Well, we can think about the solution forming in 3 steps. One thing that has to happen is we have to separate the solute into particles, whether those are ions or molecules or atoms. Separating the solute is always endothermic. Those forces of interaction, whatever they are, between those solute particles have to be overcome. So the energy change for separating that is going to be greater than 0. That's going to require energy to go in. We also have to separate the solvent particles to make room for the solute. That's also endothermic, so that's going to be a positive number. And then mixing the solute and the solvent particles together will be exothermic because energy is going to be released as the particles interact. So that's called delta H mixing. So we're separating the solute particles, and we're separating the solvent particles, and now we're letting them interact with each other. So this is going to be negative. Any questions yet? The enthalpy change, or the enthalpy of solution, is the sum of all the changes in enthalpy for each of those steps. And the overall sign can be positive or negative depending on which ones are larger, right? Because we had 2 that were positive and 1 that was negative. And so solution formation can be exothermic or endothermic. So here are 2 examples. Here's an exothermic solution forming. So we start with the individual solvent and solute. And here they are aggregated, meaning they're stuck together by their forces that hold them together. The first step was separating the solute molecules. So that requires an input of energy to separate the solute molecules. The next step was separating the solvent molecules from each other, or particles. And so that requires more energy. Now we've got individual solute and solvent particles, and we allow those to interact with each other. That's going to release energy. If the energy released is more than the sum of the energy that we had to put in, then we're going to have a net exothermic process and energy is released. In this example, again, we take the solute particles and separate them. That requires energy. We separate the solvent particles. That requires energy. And then when we allow them to interact with each other, energy is released. But here, the amount of energy released is smaller than the energy that had to be absorbed. And so this is a net endothermic process. Energy goes in to make that solution form. Of course, those individual steps are not exactly easy to measure. What we do for aqueous solutions of ionic compound is we take delta H solvent. So that's the amount of energy needed to separate the water molecules and the enthalpy change when we mix it, and we call this the heat of hydration. It's the energy change that occurs when 1 mole of gaseous solute ions is dissolved in water. And it's always going to be negative. It's always going to be largely negative. The amount of energy needed to separate the solute particles for an ionic compound is the same magnitude as the lattice energy. Remember what lattice energy was? That was when you took the individual ions in their gas state and they came together. For 1 mole of ions coming together, how much energy was released? Well, delta H solute is when you take the solid and you separate it into the ions in the gas state. So it's the same number but opposite in sign. And so then what we said earlier was heat of solution for water, heat of hydration, just heat of solution, heat of mixing, was the amount of energy that needed to be put in to separate the solute molecules, plus the amount needed to separate the solvent molecules, plus delta H mixing. So you add all those together, and this is the net difference. I said a couple words wrong there. This is what we're looking at right here. It's the net difference. This one plus this one plus this one, but this one's negative. We call these two together heat of hydration. That's always negative. The heat of solute is positive, and so whether the heat of solution is positive or negative depends on the relative strength of this. If the energy needed to separate the solute particles is smaller than the heat of hydration, the process is exothermic. When this solid dissolves in water, the solution feels warm because energy is being released. If the opposite is true, if the heat of the amount of energy to separate the solute particles is greater than the heat of hydration, then the solution process is endothermic and the solution feels cold. So a substance that has a negative heat of solution could be useful as like a chemical hot pack, because when that dissolves in water, it generates heat. There are also substances that when they dissolve in water, they absorb heat and the solution gets cold, and those can be used as chemical cold packs.